Okay, here we go. So we found this weird collection of points, some of which stay inside and some of which leave. And so what we can consider is the folks who would be staying inside forever, we call capital lambda for left inside. I don't know. And what that would be was a collection of all points in the original interval I, except then you take away anybody who actually leaves. So it's the union of all those A's. And the A's can go from n equals 0, because that's what we named the first one in the middle, all the way out to infinity. So that's the points of the unit interval 0, 1. Take away anybody who goes away, A for away, and those are the ones who are left inside forever. That doesn't mean they sit still inside forever. They bounce around. In fact, if you just think about those endpoints of A sub 49, for example, goes to 48, 47, 46, 45. It bounces all over the place and then ultimately ends up at 0. So, I mean, the questions are, what could ultimately happen there? Right? So what were those A's? We could more specifically describe the A's where A sub 0... x is in A sub 0 if f of x stays in the box 0 times, and x is in A1 if f of x stays in 1 time. Right? If you're in A1, then you take f of that, you're in A0, so you stayed in once, and then if you take f of somebody in A0, then you're history. So that's sort of the way the counting matches up, that the subscripts, x is going to be in A sub n, means that f of x stays in the box in times, which you could write algebraically as A sub n is the collection of all x's in the interval such that the ith iterate of x is inside I for I less than or equal to n. Say it stays in for n times, but the ith iterate of x is no longer in there for I greater than or equal to n plus 1. There it is. So A sub n is the set of all x's in this interval, so that if you iterate, you stay inside up until you do the function n times. Then as soon as you do it n plus 1 times, you're no longer in. And that's consistent with the way that we described 1 and 0 on the A's before. So what that brings up is a structure of a very strange kind of a set, and that puts us into our geometric detour to talk about the classic Cantor set. Some of you probably run into the Cantor set somewhere in an analysis course or a foundations kind of course before. Sometimes called the famous Cantor middle thirds set. And the idea is that it's a recursive construction. And so if you start off, the classic version of this is if you have the interval 0, 1, you divide it into thirds. And what I'm going to do is I'm going to draw different stages of the iteration of the construction here at these different levels. And so at the 0th level of iteration, you've got the whole line there. So that's got this whole piece. The whole interval 0, 1. So that's after doing the process, not yet. So what the process is you throw away the middle third, like they talk about the Cantor middle third set. So what you have is this piece and this piece, but you no longer have the middle anymore. And so at the next stage of the iteration, you chunk these into thirds, and so you have this part, and this part, and this part, and this part. And at the next level of iteration, you chuck those into thirds. So you've got that, 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 and that. So that whole line across there of those subintervals is what's the next level of the construction. And of course the key to making this something very weird is the infamous dot, dot, dot. You continue that infinitely. And so in some sense you can think about this as a geometric construction of intersections, right? You've got this, intersect that is itself, because each one's a subset of the one that came before. And so you just sort of take the infinite intersection as n goes to infinity of each one of these levels intersected with itself. And by the end down here, you keep taking out more and more and more. This is just a bunch of little kind of stuff that's actually sometimes in the literature called Cantor dust, because it is just seems like it's little specks there, right? So the idea is the limit of this iterative process is called the Cantor middle third step. And so there's two reasons we're talking about it now. One is, in particular, the construction that we just came up with in looking at the points in that set lambda, the folks that stay left inside forever when they're bouncing around. Their geometrical shape was roughly like this. It wasn't exactly thirds, it was intervals. Depends on how big the mu is, exactly how big the a sub 0 was that we talked about before. How big the little mu was. And so this one is similar in a topological sense. In this, it's got the same shape, it doesn't have exactly the same length. And so the other reason that we talk about that now is that that's both an iterative construction, which means it belongs in a discussion of things where we do things iteratively in this course. And this also gets us off in the direction of fractals. And fractals are one of those things that you hear about, chaos and fractals and chaos, blah, blah, they go together. Well, here's one place that they come up. And that is this geometrical construction is much like the geometrical structure of that lambda set. I'm going to make some more of that in a minute. So the first thing I'd like to do is sort of investigate the pattern of what's going on here. Say something about the properties of this Cantor set, named after Georg Cantor. Cantor lived, 1840s to 19 earlys, something like that, turn of the 20th century. And some people call him the inventor of set theory. That may be a stretch, but he certainly was a big contributor to the idea of infinite sets. And when you talk in an analysis course about countable and uncountable sets and different kinds of infinity, that was Georg Cantor. So let's try to analyze this set just a little bit, and we'll then return to our dynamic stuff. So you can sort of look at the number of pieces at each one of these stages, and you can also look at the total length of whatever that stage of the iterative part of constructing the Cantor set is. So in the first line, before we took anything out, there was one piece, and the total length was the total length of the interval. It was 1. In the next piece, we took out the middle in the next part of the iteration, and there were 2 pieces, and we took out a third, so the total length was 2/3. In this next stage, there were 4 pieces, and each one of those was, let me see, if this was a third, then that's a third of a third, so that's a ninth. 1, 2, 3, 4, so that's 4/9. That's how long that one is. Let's try it one more. This one has 3, 4, 5, 6, 7, 8 pieces, and each one of those was maybe a third of the length before, so that's 8/27. It's starting to look real sloppy, but let's take a look here. The pattern here is that this is 2 to the 0, this is 2 to the 1, this is 2 to the 2, this is 2 to the 3. So that means after 1, 2, 0 stages of ripping anything out, 1, 2, 3. So after n stages, we're going to have 2 to the n is the number of pieces. So what's happening over on this side, the total length is, that's just always twice as big, and that's always 3 times as big. So this is 2/3 to the 0, this is 2/3 to the 1, this is 2/3 to the 2, this is 2/3 to the 3. Gee, let me guess. When you get to the nth stage, it's going to be 2/3 to the n. I'm sorry I'm writing sideways, so it's hard for me to write this stuff down. So there are two things happening at each stage of the iteration. It's getting smaller because you're multiplying by another power of 2/3, by one more copy of 2/3, and there's going to be more and more pieces. So the two things that the Cantor set is simultaneously doing is it's getting more and more fragmented and smaller in size. And so what happens is that the properties that you can investigate about this classic Cantor middle third set is, one thing it is it's closed. Because if you think about that, each one of those intervals we were taking out, we were always taking out an open interval and leaving the edge there. So back in this case, when we took this middle part out, we left the edges to match there. So we took out an open set. That's what we removed, and we left behind a closed set. So that means you can think about the union of all the sets that we removed. You take out that, then you take out those two, then you take out those four. But each time that's a union of a bunch of open sets. And remember, open is the kind you can get away with taking big fat unions. So a union of an open set is an open set, and the complement of an open set, the stuff that's left behind, is then closed. So the Cantor set is closed. Another property of the Cantor set is that it is what's called totally disconnected, which means that it contains no intervals. So totally disconnected means that any 2 points in the set have something in between them, a hole that's not in something that's not in the set. So if there were any intervals in the set, then the 2 points would have everybody in between them is also in the set. And that's what the Cantor set does not have. For any 2 points you pick, there's going to be somewhere in between that's not included in the set. Totally disconnected. No intervals at all. And the third thing that it satisfies is really kind of interesting compared with that one, and that's yet another word in mathematics that gets reused to mean different things in different contexts. You know what a perfect number is in a number theory sort of context, but a perfect set here means that each point in the set is a limit point of other points in the set. So every point's a limit point. Okay, a limit point means, if you remember one way we talked about open sets and closed sets and limit points and things, a limit point is sort of like, remember our old buddy, if you look at the collection of points 1 over n, that you get a half, a third, a fourth, a fifth, a sixth, blah, 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 blah. The union of all those guys, 0 is a limit point of that, right? So in a perfect set, every point acts like that 0 acts. See, now these guys are limit points because they've got, for the set, there's the set of all those 1 over n's union with 0. And 0 is a limit point for that set, but the other guys aren't limit points of other folks. They're just their own kind of standalone limit points of a constant sequence of themselves. But there's nobody clustering there. That's sometimes called a cluster point. That means arbitrarily. See, if you take this 0, arbitrarily close to 0, no matter how small an interval you pick around it, there's other guys in there. And so one way to say that this property of perfect can be described is a point in a set is perfect if arbitrarily close to it are other points in the set. Now when you put that with number 2 totally disconnected means arbitrarily close to a point in the set are points that are not in the set. So that's a really bizarro combination. That if you take any point in whatever this set is, and you take an interval in there, no matter how small, then inside that neighborhood, there are going to be other points that are in the set, but there are going to be holes. There are going to be other points that are not in the set. There are other points because it's perfect, and there are other non-points, points that aren't included in the set, because it's totally disconnected. And those are 3 properties that this classical Cantor set has, which is sort of bizarre, right? So the Cantor set is the beginning of an edge of talking about things like fractals, but I want to mention just one other weird thing about the classic Cantor set, and that is the total length is 0 because, well, duh, there are no intervals, right? And that's also consistent with this description that we had about the total length in the iterative construction. Each time in the iteration, the construction is 2/3 as big as it was before. And if you take 2/3 to the nth power and let the n go to infinity, that means that the total length is going to 0 as you take the limit of that process. So the total length of the Cantor set is 0, but if you've looked at other things that Cantor looked at, things like countable and uncountable sets where the integers are countable, the rationals are countable, but the reals are on an interval are uncountable. The strange thing here is that the Cantor set is also uncountable. So the way I always like to say that is the Cantor set a large set or a small set? And the answer is it depends on what you mean. Because it's a small set in terms of total length. The total length is 0 because every point is a standalone point. But there's so many of them squeezed in there close to each other, and that's the perfect part, that they're uncountably many. It's more than just, I mean, just think about the rationals, how tightly packed they are in the interval 0, 1, and yet they're still only countable. This Cantor set thing ends up being uncountable. Well, this is the edge of talking about fractals. And a fractal is a set. I mean, you run into chaos and fractals together a lot. Classic fractals were defined and played with by Mandelbrot. And there are two sort of defining characteristics of fractal sets. One of them is self-similarity. And self-similarity means that a proper subset of the set is somehow equivalent in some mathematically describable way to the whole set. And if you think about that Cantor set, the classic Cantor set, right? I mean, if you take out this middle third and it's gone, and you just got these two guys that are left, then that's exactly what's happening there too, right? And so you could map that to there, and map that to there, and what happens is that you could map this subset, the interval from the part of the Cantor set that lives in the interval 0, 1/3, you can map homeomorphically. It's a homeomorphism like we talked about in the earlier section. You can map that onto the entire interval 0, 1 in exactly a 1-to-1 correspondence. So there's a homeomorphism between a proper subset of the set and itself. And the behavior inside each one of these then is also the same as the behavior inside there, which is the same as the behavior inside that larger piece. And that's the self-similarity part. In fact, you can do that by the function L of x. L for a linear transformation is 3x. It takes anybody there from 0 to 1/3 up to its corresponding, the counterpart in 0, 1, not in the intervals, but the Cantor set part that lives as a subset of those intervals. So, anyway, maybe a good time for a fractal detour. The Cantor set in particular, but fractals in general. Sorry, I got distracted. So fractals would be a great source of projects. The other sort of characteristic thing about fractals is that they could end up having fractional dimension. And I should say that the idea of fractals in general and lots of different definitions of dimension, of the dimension of a set and the dimension of a space. And either one of those would be great project ideas, either going fractals or going dimension or playing around with those in particular. That dimension stuff is often about scaling and counting. So here's a brief detour into dimension. Okay, dimensions of sets that we understand. So for example, if you take the interval 0, 1 and you scale that by a factor of a third. You take something that's a third as big, so 0 to a third, like that part we talked about before. And don't iterate, don't just do this once. Then it would take 3 of those put together. There's one there and one there and one there to get back to the original size of the set, right? So you can think about that as going from the smaller to the larger is scaling by a factor of 3. And then to put those smaller scaled factors together, it's almost like to go from the big one to the small one, we scaled by a third. But then that was going that direction, but in going back up, then you scale by 3. When you get the smaller ones to piece them together to make the bigger one, then the number that it takes the number of them it takes to put that back together is 3. And so there's something about that 3 scaling factor to go from small to large, and the 3 piecing them together that we might want to try to connect together. So that's one case. Consider something two-dimensional, like just a square. Think of it having a unit length on one side. And scale that by a factor of a third. It's sort of like making these pieces a third as long and that a third as long. And so that's kind of in an appropriate dimension. And see, that's what we're trying to define, is dimension, right? But we just so used to thinking of that as two-dimensional, then we scale in one dimension, we scale in every dimension, whatever, by a third. Then in that case, you can think of the scaling. The scaling factor is 3, but then the number of pieces that it takes to put those scaled guys back to make the original guy is 9. So there's something about the connection between the numbers 3 and 9 that has something to do with this being two-dimensional. Unfortunately, these all didn't fit on the same page, so let me see if I can do this one more time. And that is, suppose you've got a cube, and you want to chunk that, you want to scale that by a factor of a third. So you cut that into thirds, and you cut that into thirds, and you cut that into thirds. So well, then there's that way, and there's that way, and there's that way, and there's that way, and there's down here, and there's back there. Looks like a Rubik's Cube, except it's so badly drawn and it's not colorful. So what happens is the scaling factor here, you're scaling by a factor of 3 in each direction or something, I don't know. And then the number of them ends up being 27. 3, 6, 9, blah, blah, blah. You count all those up. And so there's something about the relationship between that 3 and that 27. And, of course, the thing is that 3 cubed is 27. Back here, 3 squared, was 9. And over here, 3 to the first was 3. So it seems like this ends up being the appropriate thing that corresponds to our intuitive idea of what dimension ought to be. So what it looks like we have is scaling factor. The smaller to bigger scaling factor. Sometimes you'll see this, they'll say a third is the scaling factor, and then the formula will take 1 over a third and it gets you back to the 3. So it looks like what's happening is the scaling factor taken to the power of what we always think of as the dimension gets us back to the number of pieces. It takes to put together from those scaled down pieces by the scaling factor, the reciprocal of the scaling factor, the number of pieces that it takes to reconstruct the original piece, and that seems to be, we could take the scaling factor to the dimension power and you get the number of pieces. And so that is sort of this, I don't know, intuitive analysis of what our traditional ideas of dimension ought to be. Well, if you want an expression for d, then you want a logarithm on both sides here, right? So it's natural log of s to the d is natural log of n. And then, of course, one of our favorite properties of logarithms is if there's a power on a guy inside, you can whomp it down in the front. So that's d natural log of s equals natural log of n, which means if there's a little corner left here, we get d is natural log of n over natural log of s there is a formula for dimension in terms of this geometrical construction way of thinking about it. And if you check that with the 1s and the 2s and the 3s that we talked about before, it checks out. Just if you don't believe the calculation, it actually does work. So what I'd like to do now is try to apply that to the Cantor set. Where in the Cantor set, you've got some subset of that where the middle ends up being gone. It's not there. And then you got the middles here are gone, and you got some leftovers, and the middles there are gone, and so the Cantor set is all caught within the part that I didn't just squiggle out. But remember when we discussed that homeomorphism idea, what we said was that this part right here, the part of the Cantor set that lives between 0 and a third, and there's, it's a subset and a subset and a subset and blah, 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 you're throwing away stuff. That part's homeomorphic to that part. Well, that means if we did a scaling of 1/3, then to scale back to the big one is a scaling power of 3, just like in the example that we did before. But then if we take that third scaled thing and want to add them together to build the original guy, the number of pieces is only 2. There's the chunk that fits there, and there's the chunk that fits there, and this is nothing. It's not there. Right? So if you scale that down by 1/3, it takes 2 of them to reconstruct the original set. And if you scale down by 1/3, then the scaling factor we were using in our conversation was what it takes to go back up. It would be multiplying by 3. And so that formula that we just looked at says that the dimension of this set, this Cantor set that can be decomposed and reconstructed by this scaling factor and number count, ought to be, well, the natural log of the number of pieces divided by the natural log of the scaling factor. So in this case, it's the natural log of 2 over the natural log of 3. That's the dimension of the Cantor set. Bump the camera. Sorry. And I don't know those numbers off the top of my head, but what I do know is it's positive. It's between 0 and 1. Right? That would have to be a 3 for that to be a 1. So the dimension of the Cantor set is less than 1 but bigger than 0, and it's a fractional dimension. The idea is it's not one-dimensional like a line segment would be because we took out enough stuff that there's not enough left to be fully one-dimensional. But we don't have any intervals left, but we have enough accumulation points, enough of those limit points clustering close to each other. They stay so close, everybody is a limit point. They're crunching together so close that they accumulate to being more than a point, of being 0-dimensional. And the dimension of the Cantor set is then between 0 and 1, which is really weird. Okay, so if you're into this fractal detour, then let me just mention a couple of other constructions that are examples. One of them is called the Sierpinski gasket. The Sierpinski gasket. And it's also a start with something and then remove stuff kind of construction, just like the Cantor set one, but it starts with an equilateral triangle. And then what happens is you just take the midpoints of the 3 sides and connect those, and what that gives is an equilateral triangle, and you remove the middle third, the middle triangle, and you have 3 pieces that remain. And you can see what's coming, right? Each one of those is just a smaller version of the original, so you repeat. You slice it into 4 triangles, and you take out the middle one. You slice that into 4 triangles, and you take out the middle one. And now you do to each one of those what you've done to the earlier ones. You take out the middle chunk of that one, and 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 you continue. And you take the limit of that as the number of iterations, the limit of whatever that construction process was. And in the limit, that thing is called the Sierpinski gasket. And so from that same sort of analysis that we did before, one thing that you can get is that you take out so much that the area here is 0. Just like before, the total length of the Cantor set was 0. But the dimension is a little bit strange, because if you think about one of those being equivalent to the original guy, what did we do? We took the side and cut it in half, and we took the side, we cut it in half. So the scaling factor here, again, the small to large version of the scaling factor is 2. But the number of pieces to put this back together was 1, 2, 3, because the middle one's not there. It's not part of the construction, so the number was 3. So the definition of the dimension is the natural log of the number of pieces divided by the natural log of the small to big scaling factor. So in that case, we have natural log of 3 over natural log of 2. So in this case, the fractal dimension, or the fractional dimension of the Sierpinski gasket, it's not two-dimensional anymore. It started out as this two-dimensional filled-in rectangle. Well, I'm sorry, triangle, but we kept yanking stuff out over and over again until we took so much stuff out, it's not two-dimensional anymore. But the stuff that's left, behind didn't get back to being just one-dimensional, because it bends. If you can imagine what's left here, it bends back on itself so many times that it doesn't get quite small enough to be one-dimensional. It's in between. Don't you just love this fractal stuff? So obviously fractals would be a good detour for someone to do a project on it. They're applied to things because, after all, why did we start down this pathway? It's what that set lambda looked like that came out of our quadratic map. The folks that stayed behind end up having this fractal kind of structure because the theorem that we want to get around to proving is that set lambda is a Cantor set, where a Cantor set is a set that has those properties that we said the Cantor set has. Before we do that, let me just do one more example just that I don't misrepresent this whole fractal thing, and that's called the Koch snowflake, or the Koch curve, called various things. And this one, just to show the alternative, the other two constructions that we did with both the Cantor set and the Sierpinski gasket were removing, they're sort of subtractive construction. And the Koch snowflake, or the Koch curve, is an additive sort of construction. And the same thing happens with this one in the sense of starting with a rectangle. That's twice I've called those rectangles. An equilateral triangle, but we're just talking about the triangle, not its contents, not its interior. So with the Sierpinski gasket, I don't know if I misspoke, but we were talking about the triangle and its interior, and then you throw stuff away and you see what's left. So in the snowflake, we're taking the actual boundary, and that's all, not the interior. So then what you do is you take each of the three sides and you cut them into thirds. Sounds kind of Cantor-ish. And what you do is you throw away the middle, and what you do is replace that by connecting. You take a piece that's exactly that long and you put two of them right there. So it's 1, 2, 3, 4 compared to the 1, 2, 3 it used to be. Same thing here. You got one, you put one the same size there and the same size there, and then there's the fourth one. So it's 1, 2, 3, 4, and 1, 2, 3, 4. And so now it's just the outside of that. But again, that's only one step in an iteration. So what you do next is you do to each one of these edges as you did to the previous edge, which was you throw away the middle and you put one of those in. You throw away the middle and you put one of those in. You throw away the middle and you put one of those in, over and over. And so the outside there, so the Koch curve ends up, then you do it there, then you do it again, and you do repetitively. So it kind of goes up there, it's wiggly, it's wiggly, it's wiggly, it's wiggly, it's wiggly, because you keep doing that over and over again, and so it's just this outside thing with more and more spiky kind of stuff going on. You can see why they call it the snowflake. It's kind of got that six-fold symmetry like snowflakes do. So here's the idea then. Think about this construction in terms of the recursive construction that you do on one edge. So think about that as one edge and you do it to the other two also. what you do is you take it and you cut it into thirds, and you replace that by that. And you do that on all three sides, and you recursively do that again. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So anyway, a little sloppy right there. So the idea is to go from here to here. What you've done is you scale this down by a third, which means the version of it that we've been using is going that direction. We call it a 3. So the scaling factor is a 3 to get from the small one back to the large one. But the number of pieces that it takes for the scaled guy to put it back together is 1, 2, 3, 4. In fact, the new Wiggly version, Wiggly 1, Wiggly 2, Wiggly 3, Wiggly 4. So it's 4 pieces. And so the dimension of the Coke Snowflake is going to be the natural log of 4 over the natural log of 3, which again, that's a 3, is between 1 and 2. But we got at it from a different direction than we did before. So if you thought about it, we started this with an equilateral triangle and just the boundary of the triangle, not the interior. That's one-dimensional. And we just kept adding more wiggles and wiggles and wiggles until it wasn't one-dimensional anymore. There was so much folding back on itself that then it got more than one-dimensional, but it didn't fold back on itself enough to get all the way up to 2 dimensions. But that came by additively instead of removing things. And the two things I would mention in this context, that the weird sort of geometrical, feels like a contradiction going on here, is how the length of the boundary of this thing, every time you do the iteration, it's 1, 2, 3, 4, it's 4/3 as long as it was before. And so if you do that n times, and you let n go to infinity, means that the boundary of this thing is infinitely long. Boundary has infinite length. I mean, just look at it, right? That's what happens. Every time you add on a length it's 4/3 as long as it was the previous part of the iteration. So this thing is infinitely long, but man, I can draw a circle around that has a finite area. So that means the stuff inside has a finite area. So that's the thing I like about the Coke Snowflake, and that is that it's infinitely long boundary to a finite area. Seems kind of bizarre. The thing I'd mentioned in passing before we return back to the general flow from this detour is if you're interested in some more historical little detour, the Peano curve. It's also called a space-filling curve. And that's a construction from a century ago where you bend back on yourself enough that you do a geometrical construction so that the same kind of calculation gets you that the curve bends back on itself enough that its dimension is actually 2. And so it actually fills the 2-dimensional space. Okay, time for a pause, and we'll get back in just a minute.